So thank you for inviting me to give this talk about cosmology. This is only a very introductory survey of some of the current research in cosmology and why we're interested in cosmology. So let me try to answer this question I posted as the title of the talk. Why should we care about cosmology? One answer is that, well, even baby cares, right? Even small children, they will ask questions like, why are there stars? How were we made? How old is the universe? What happened before the Big Bang? Nowadays, they teach Big Bang in kindergarten. The next one is irrelevant. The next one, Kawa, this is Kawa's little son. And he asked me to put this in. Are black holes edible? Okay. So I think all of these are cosmological questions. So the answer to the question why we should care is that because we care. We don't need to know why we care. We just care. Let me give you another version of the answer, maybe slightly more professional. As physicists, we know that experiments are all important. And you can think about cosmology or the evolution of the universe as the biggest experiment ever, the grandest experiment ever. And what's special about this experiment is that you can actually observe what's going on in this experiment at different time frames. This is normally not possible. So for example, if you go do an experiment in a collider, you collide the protons and then all you know are the final products. You have to guess what happened during the interaction and so on. Not so with the universe. Everything is there. Everything is for us to observe. And in fact, if we want to understand the evolution of the universe, we need to get all the physics right. So this is a tough experiment for us to build the theory to explain the experimental results. And along the way, there have been many, many surprises, which usually stimulated new questions and new observations. So as of today, we could directly observe what happened in the universe all the way from today. So the horizontal axis is a timeline. We could actually observe what happened in the universe from today all the way back to about 400,000 years since the Big Bang. That's the time point when the cosmic microwave background was emitted. So there have been precision measurements of these CMB. And along the way, we have understood a lot about the evolution of the universe, starting from at least this point, and actually a little bit earlier than this point. I'm going to talk about a grand conjecture about how the universe evolved this way, but I found it really quite interesting. This is a conjecture by Peebles in a classic paper, 1965. Peebles, of course, he won the Nobel Prize 2 years ago. The conjecture is that all these galaxies, all these stars that we see today, they were seeded from the fluctuations in CMB. There were tiny fluctuations in the cosmic microwave background. And these fluctuations in the CMB themselves they are originated from the quantum fluctuations, which got amplified by this inflationary phase. So the tiny quantum fluctuations get amplified once to be the CMB, which we can observe, and then amplify again during this evolution by gravity and becoming all the galaxies and stars and us. So this grand conjecture would say everything we can observe today in the universe, they got developed from some initial quantum fluctuations. This is just one example of why cosmology is interesting. Now, this is still a conjecture. We don't know whether it's correct or not. But in any case, I think as scientists, as physicists, we really like to know the origin of everything. And pretty much the same as this childlike questions. Why are there stars? How were we made? And so on. Now, to show you that we can really observe the universe at different time frames, this is one picture to show what I meant. This is a real picture taken by the Hubble Space Telescope. Here you see many different galaxies, and some of these galaxies are very far away, 13 billion light years away, more than that. Okay? So the light travel about 13 giga-years before arriving at our telescope. In other words, by observing these galaxies, which are far out there, we're really observing the state of the universe when it was very young, like less than 1 billion years old. We're really looking all the way back in time to see how these galaxies developed. And of course, as I mentioned, we can already measure to high precision all these fluctuations in the CMB. So we can really look all the way back to the 400,000 years since the beginning. Now, furthermore, we also had the theoretical framework to describe this evolution. Today, we understand the expansion of the universe by general relativity. In general relativity, space and time are dynamic. So space can expand, can also contract. And we visualize the expansion of space by putting some grids in empty space. And we specify the relative size of the grids at different times. So for example, this A, which we call a scale factor, might be 0.5 at some time, and then it got doubled after some time. This is how we describe the expansion of the universe, which is the expansion of the empty space. And we assume that this expansion is uniform in space. The change in A is the same everywhere in the universe. Even more remarkably, the equations that describe this change in the scale factor was already derived in 1922, more than 15 years before anyone observed this expansion of the universe. So there are two very simple ordinary differential equations. So even E1 students can solve them. And we can, today, the observational data actually agree quite well with these two so-called Friedmann equations. If you have some free photons, like the CMB photons, then the wavelength will also expand together with the scale factor. And since the wavelength is inversely proportional to the energy of the photons, we know that the temperature of the universe also goes inversely proportional to this scale factor. Okay, Let's try to answer 3 of the baby questions. Why are there stars? How were we made? How old is the universe? In fact, I'm going to combine the first 2 into one professionally sounding question. How was stuff made? And I'm going to change the first question, how old is the universe, into an equivalent one, which is how fast does the universe expand? I'll spend much more time on the first question and just very briefly on the second one. Okay, since we know how the universe expanded, according to the Friedmann equation, we know how the temperature depends on time. So we can look back in time and we can map out the temperature of the universe. At different temperature, according to the physics we know, we can specify how the state of matter would change. So I'm going to discuss briefly about the formation of protons and neutrons in the formation of the light nuclei. I'm going to skip the formation of atoms because that's easy stuff. And then I'll jump directly to the formation of galaxies. For the formation of protons and neutrons, we need this theory for strong interaction, QCD. For the light elements, we need both a strong interaction and weak interactions. For atoms, we need to know electromagnetism and a little bit of quantum mechanics. For galaxies, we need to understand gravity. So here you see that all the 4 fundamental forces come into play. This is what I meant when I said that in order to understand the evolution of the universe, we need to get all these physics right. If we didn't understand QCD, we could not describe the formation of protons and neutrons. And then, of course, we cannot talk about the rest. Let me start with protons and neutrons. So of course, with QCD, we now know that protons and neutrons are what we call hadrons. They are just bound states of quarks and gluons. So if you could look inside a proton, you see infinitely many quarks, antiquarks, and gluons. It's a really messy, relativistic, and nonlinear field theory. The strong interactions among the quarks and gluons produce a tightly bound state, such as a proton or neutron. We have numerical tools to calculate QCD. These are called lattice QCD calculations. So for example, today, we can actually calculate the hadron masses to agree with within 2% of the experimental measured values. So we think we really can calculate all these messy bound states. There's an important properties of QCD called asymptotic freedom, telling us that when the quarks and gluons, they get very, very close together, or when they are at very high energy, they don't interact. It becomes free. So this implies that if we could heat up all these hadrons to very high temperature or very high density, then the quarks and gluons will be set free. That transition temperature is about 140 MeV. This is a value calculated by lattice QCD. We know this value very well, which is about 10 to 12 K. So that happened about 10 to the minus 5 seconds since the beginning of the universe. So if we zoom into this region, we are pretty sure, because of our knowledge of QCD, that around this time, the universe would have gone through this phase transition from quark matter, basically free quarks and gluons, becoming the hadrons that we know, the protons and neutrons and so on. So now we live in the low temperature universe where we only see the protons and neutrons, but in the earliest moments of the universe should be filled of these quarks and gluons. Today, we can actually do experiments to probe this phase transition. And there are two facilities in the world to do this. One in Brookhaven called Relativistic Heavy Ion Collider. The other one is, of course, the famous Large Hadron Collider. This is a simulated picture of what the LS detector at the LHC would see in a typical event. So typically, at LHC, they would collide two heavy ions, such as two lead nuclei, at very high energy. And then after the collision, they would create a fireball. And the point of the fireball is that it should reach a temperature above the quark-gluon transition. That fireball expanded rapidly, cool down, and all we can see in the detector are the final state products, all the particles produced after the fireball cooled down. So we do not see the free quarks and gluons directly. But still, such kind of mini-bang experiments allow us to study quark confinement, properties of this quark-gluon matter, as well as the hadronization phase transition. So this is still an ongoing experiment, and we're still learning about all these. And they go into part of the answer of how stuff are made. This is how we try to understand how protons and neutrons are made. Let me go to the next step. Okay, so you have the protons, neutrons, electrons. How do you form the different nuclei? Okay, so now we're going to the topics commonly called BBN, Big Bang nucleosynthesis. So this is a schematic picture of what happened in the first 3 minutes of the universe. In the beginning, we have the free protons and neutrons. They were already created by the quarks at the first 10 to the minus 5 seconds. The neutrons could either do beta decay and become protons, or they could be captured by the proton to form deuterons. So there's a competition here between some nuclear reaction and beta decay. Once you form the deuterons, you can go on to produce helium-3 and helium-4. And a tiny bit of beryllium-7 and lithium-7. These are all the nuclei that were produced in the first 3 minutes. Once you pass the first 3 minutes, the temperature became too low. There will be no more nuclear reactions until you light up the first stars. So these were all the elements produced in the Big Bang. Now, I won't go through the details here. This is actually rather old calculations already. All these nuclear reaction rates are well known. We can either calculate them theoretically once we know strong and weak interactions, or you just go measure them in the lab. So once you know the reaction rates, you can easily calculate the relative abundances of these different products. This was done in 1948 already in this very famous paper called alpha beta gamma paper. I think it was deliberate that it was published on April's Fool Day, 1948. Why did I say it was deliberate? Well, Gamow is a really humorous guy and also very, very bright guy. The story was that Alpha was Gamow's PhD student. So Alpha was actually working with Gamow to do these calculations. But then Gamow found that it's no fun to have Alpha and Gamow. We need beta. We need alpha, beta, gamma. So he dragged Hans Bethe to be an author, just put his name in. Hans Bethe did not do any calculation for this paper. He just listed them so that he would make alpha, beta, gamma. It's a really funny guy. And he did several other things that are very important. I think he deserved at least 3 Nobel Prizes. Now, the results of the calculations was really quite remarkable. You can predict the abundances of different elements like helium-4, deuterium, helium-3, lithium-7, and so on. So the color lines represent the theoretical calculation as a function of the baryon density, number density of baryons, number density of protons and neutrons. So all these abundances depend on the number density of baryons, of course. And then you can do observations. So the observational data were indicated by these boxes with the uncertainties. Okay? And the blue band represents the CMB measurements of the baryon density. So you could fit all the abundances for one number, which is baryon number density. And there is one common solution. And this already told us in 1948 that in the universe, the numbers of protons and neutrons, or the masses, they contribute only a tiny fraction of all the matter. There's a lot more matter out there which are not the baryons, not the protons and neutrons. The same fitting also told us that there will only be 3 types of light neutrinos. If you change this number, you could not fit everybody. This results, the number density of baryons, turn out to agree with other measurements much later, such as the CMB measurements I told you about. So think about this. These abundances of the light nuclei, they are light signals from the first minutes. And we could actually measure them, compare with theory, and learn something very important about our universe. For example, the existence of dark matter. Now, even today, you can still make use of BBN to constrain different kinds of theories beyond standard model theories. So I'm selfish, so I just pull a calculation done by my ex-MPhil student, Baojiu Li, in 2005. This is just part of his MPhil thesis. So it should be quite obvious that these calculations must depend on the fine structure constant. And we're talking about the first 3 minutes of the universe. Who knows? Maybe the fine structure constant at that time will be different from the value of the fine structure constant today. So we could actually redo these calculations, assuming that there might be a deviation of a fine structure constant then and now. And we make use of the observational data to constrain this deviation. We could constrain it to the level of 10 to the minus 3. Just to give you an example, how we could make use of cosmology to learn something about fundamental physics, that indeed the fine structure constant seems to be a constant at least to this level, 10 to the minus 3, throughout the history of the universe. Okay, so now with the protons and neutrons and we have the light elements, I'll skip the atoms. Atoms are simply made by the protons capturing the electrons, and that's just year 1 physics. Because of time limits, let me go directly to the next part of the answer to the baby question. How was stuff made? Okay, so how were galaxies made? We see all these galaxies in the universe today. How were they made? This is, of course, a very important question, not just for cosmology, but also for astronomy. And I will only give you part of the answer. So today we know that what you can see, all these galaxies, or in cosmology, we call them baryons, are really hidden into much larger structures formed by dark matter. Okay. So here you see all these globs. We call them dark matter halos. You cannot see them. They're not the galaxies. And these dark matter halos also seem to form a very large structures of a very large network-like structure. And according to Peebles, the galaxies were formed by amplifying the small fluctuations in the CMB. This is a real picture taken by Planck. The red dots represent slightly hotter CMB temperature. Blue parts indicate slightly colder CMB temperature. This is an all-sky projection measure. The small fluctuations in temperature is about 10 to the minus 5th. The average CMB temperature is about 2.7 K. Okay. So we can really measure all these small fluctuations in CMB temperature. And according to Peebles, these fluctuations got amplified by gravity into what you can see today. That's really quite remarkable. And furthermore, the CMB fluctuations, they grew from quantum fluctuations during this hypothetical inflationary phase. I won't have time to talk much about inflationary models today, but this is, of course, a hot topic of cosmological research today. Well, let me tell you at least the second half of the story. We can really go through rigorous calculations to show how these small density fluctuations, at least from the CMB era, how they got amplified by gravity to form the large-scale structures that we can observe today. The theory is, we know the theory very well, and we can do the simulations because we're talking about highly nonlinear amplifications. We have to make use of large computers to do these simulations. So here I show you one simulation done by my previous PhD student, Balong Cheng. to show you how initially almost uniform matter distribution would automatically collapse because of gravity to form these highly nonlinear structures. Here in these simulations, we only have dark matter. And the dark matter produce enough of the gravitational potential well for the baryons to fall into the potential wells and condense to form the galaxies. Okay. So without the dark matter, we would not be able to form all these galaxy clusters and galaxies. And the large-scale structures, which you can measure very well today, will be completely wrong. So we really need the dark matter, but we don't know what the dark matter is. Just one page to show you the theory behind these n-body simulations. Okay, it's actually very simple conceptually. We just follow the Boltzmann equation with no collision term, because we're talking about the dark matter. You can neglect the interaction, except through a common mutual gravity. So we have a Poisson equation here. F here describes the distribution function, the phase-space distribution function of the dark matter particles. Okay. So the n-body simulation is just one efficient way to solve these Boltzmann equations. We can really follow the evolution of the distribution function, and therefore we can calculate the density, how the dark matter density would change in time. Many people have been doing these simulations, and now our standard cosmological model, the so-called lambda CDM, can really reproduce the observed matter distribution statistically based on collisionless cold dark matter. Okay. We can really show how initial very small fluctuations get amplified into the structures we see today. So this is also a very famous work, and Springle and White, they all got Shaw Prize and so on. Now, however, this is not the end of that story, because even though the large-scale structures agree very well, if you look into details, okay, so you can take some dark matter halos, analyze its density distribution, the density profiles of the dark matter halos is wrong. Lambda QCD, the standard model, predicts a cuspy profile, meaning that the density should go to infinity at the center of the halos. Whereas observation prefer a core profile. The density should become a flat density at the center of the halo. So you can measure the rotational velocity in the dark matter halo as a function of R, and the data points clearly disagree with the lambda CDM prediction. This is known as the core cusp problem. Furthermore, in lambda QCD, you typically predict on the order of 1,000 of satellite galaxies for Milky Way. But we only observed 50. So again, clearly there's large discrepancies between lambda CDM and observation in small scales. And most of these missing satellites, you might be wondering, oh, maybe we only saw 50 because there are many, many deep ones that we don't see, right? Well, according to lambda CDM, there should be, among these 1,000 satellites, many of them should be very massive, but we're actually missing the massive ones. And if the dark matter halo is massive, it should also host many stars. So there's no way they have escaped detection. So Nowadays, many people are trying different ideas to cure this problem, to maybe replace lambda CDM with other models of the dark matter. To cure these problems in small scales, okay? We want to understand both the large scale and small scale distributions of matter. Okay? I just give you one example, just because this is interesting. It's called fuzzy dark matter. It was proposed by Wayne Hu already 22 years ago. But recently has also become very, very hot. So theoretically, whether you're talking about string theory or in QCD, we need scalar particles. There should be a lot of scalar particles in nature. Right? So these are boson. So for example, there's a famous problem in QCD. How come QCD does not have CP violation? Okay? To solve this problem, there should be a new scalar particle called axions, QCD axions. People have been looking for it for a long, long time. If you find it, you solve the QCD CP problem as well as the dark matter problem. Now, these scalar particles have light masses. So for example, people now usually talk about 10 to the minus 22nd eV or so. And therefore, they have a long de Broglie wavelength, about 3,000 light years long. So these are not the kind of particles you normally have in mind. And that's also why many experimental attempts to detect dark matter could not find them because your detectors are just way too small. Okay? Even the Earth is way too small compared to the de Broglie wavelength of these fuzzy dark matter. Such kind of FDM would obey the Schrödinger-Poisson equation. So the ordinary Schrödinger equation coupled to gravity, so Poisson equation. And people found that the ground state of such Schrödinger-Poisson equation will represent solitons. And these solitons have core density profiles. So this would agree much better with observations than the lambda CDM. My ex-PhD student, Jiajun Zhang, actually did some cosmological FDM simulations to compare with CDM. And you can see that indeed, you can reproduce the large-scale structures, which is a success of CDM. But if you look in the small scales, the FDM indeed produce much smoother structures and much less structures, much less satellite galaxies, for example. So this is a promising candidate, okay? But there are many other possible candidates for dark matter. This is another area of very active ongoing research in cosmology. Okay, I'll skip that slide. All right, so baby is happy with the first question. Okay, I now know how stuff were made. Oh, but wait, baby also know. How come we have not been annihilated? What do I mean? Well, you told me how you produce protons and neutrons. You told me how you produce elements and galaxies. But how come you don't produce the antiprotons and antineutrons as well? Okay. In fact, according to this picture of the Big Bang, which you learned in kindergarten, early universe is pure energy. And when energy gets converted into matter, so for example, here, the photons got converted into an E plus E minus pair. You should have equal amounts of matter and antimatter. How come I only see matter basically today? So this is a big open problem with cosmology. And basically, we need a tiny asymmetry, matter minus antimatter divided by the sum, to be of the order of 10 to the minus 8 to explain the current asymmetry. So technically, what we need is a CP violation. Basically, it just says that some interactions treat matter and antimatter differently. I won't have time to go into details, but currently people are looking actively in two areas. This is a table of the elementary particles in the standard model of particle physics. So naturally, you look for CP violations in the interactions of the elementary particles. We now know that there are CP violations in the quark sector, but they're way too small, not enough. Okay? No CP violation, no known CP violations in the electron, muon, and tau. Okay? Maybe in neutrinos, we don't know yet. And maybe in this newly discovered Higgs particle. Okay. So these two are the least understood areas, least understood particles, and most promising places to look for CP violations. Our team at CUHK have been actively involved in an experiment in Daya Bay, nearby reactor power plants, where we could study many neutrinos. Okay? We could not directly measure the neutrino CP violation, but we measured something that's like the first step to establish the possibility, the feasibility to do this. So the Daya Bay experiment is done. And now the next generation of experiments, such as one in Japan called T2K, is now actively pursuing that direction. In 2017, they already see some hints of CP violation in the neutrino sectors. So they have to prepare neutrino beam and anti-neutrino beam, shoot it from one place in Japan through 300 kilometers underground to detectors in Kamioka. This is a T2K team. I just want to show you this kid, Ming Chung Chu, who graduated from us, in fact, from my group. He was actually in the Daya Bay experiment as well. 2020, T2K published this Nature paper, giving us now the best constraint on the CP violation neutrinos, which is parameterized by this delta CP. Okay? If delta CP is 0 or pi, there would be no CP violation. And now T2K ruled out these either 0 or pi at 95% level. And in fact, right now, the data prefers maximal CP violation. Okay, so if delta CP is pi, then you pi over 2, then you have maximal CP violation. New experiments will confirm this, but looks very promising. What about the Higgs? Well, you all know there's only one facility that you can study the Higgs, right? The LHC. We are also, the Hong Kong team is part of the Atlas collaboration, and we have a huge detector to detect the Higgs. Okay, so you can collide protons at high energy. Sometimes you produce a heavy particle like the Higgs. And the Higgs is nice because, well, first of all, nothing much is known about it. So maybe it has a large CP violation. And furthermore, according to the Higgs theory, it couples to massive particles. So hopefully, it also provides a portal. So because it couples to massive particles, maybe couples to all these massive but hidden particles like dark matter particles. Okay, so the CUHK team, particularly Professor Tom Chang, we are actually leading the ATLAS measurement of the Higgs decaying into tau to see whether there are any CP violations in such events. Okay? So if you want to know more details, go ask Tom about it. I'm very proud that it's a team from Hong Kong actually leading this analysis. Okay, I have only, I'm already overrun. So let me spend the last 2 minutes to talk about the last question. How old is the universe, or how fast does the universe expand? Okay. Now, I told you about the Friedmann equation. You could solve it and you reproduce this curve, which is A versus time. A is a scale factor. So today we usually define A to be 1. Earlier time, A will be smaller, so the universe is expanding. And in the future, it would expand even more. This is taking the lambda CDM with the observed values of the cosmological parameters. This is the solution we got. So if you measure the slope of A versus time at now, we got the expansion rate of the universe today. Okay. So we define a Hubble parameter, which is A dot over A. And by Friedmann equation, we know that it's controlled by the energy content in the universe, including the so-called dark energy. If you want to calculate the age of the universe, you just integrate this curve all the way from A equals 1 to 0 and find the total time. So that's easy to do. And you find that good approximation. It's just 1 over h naught. H naught is a Hubble parameter today. And the standard value is 13.8 billion years. However, in recent years, it becomes more and more problematic that different ways to measure this Hubble parameter give rise to large discrepancies. Okay? So CMB measurements give us a value around 67, whereas supernova measurements, we call local measurements, give us a value 73. And there's a 4 sigma tension in the differences. They simply don't overlap in H naught to within 4 sigma. And this tension is actually growing. So that worries a lot of cosmologists. This is considered to be a big problem now in cosmology. I don't know the solution yet, okay? But I just like to tell you something very interesting done by Terry. The paper will come out very soon. It's been already accepted by Physical Review D. So Terry just took the Planck data, CMB data, and cut it into different half skies, pointing in different directions, and just do the standard fitting to measure the cosmological parameter. So for example, I show you the Hubble parameter, H naught, as a function of the different direction dotted to a best fit dipole. Okay? So basically, the data shows a very significant dipole form of the H naught. In fact, we saw this dipole form for all cosmological parameters. It seems that if you look in different directions in the sky, the Hubble parameters are different. And the variation in this Hubble parameter has the same amplitude as the Hubble tension that I told you about. It ranged from something like 65 to something around 70. We don't know why it's so, but this is just what the data is telling us now. This might be either something very important that we need to revise fundamentally our understanding of cosmology, or it could be some hidden systematic errors in the CMB measurement. Okay. Furthermore, there are about 6 cosmological parameters you can measure with CMB. H0 is only 1. Turn out that all of them generally align to one direction. So there seems to be preferred directions in the universe, if you just take these data at face value. This might be a hint that we really haven't understood something about the CMB. We are puzzled too. All right, so I think I'll just summarize. I think we have entered a golden age of cosmology. I told you about formation of stuff. Okay, we have a good framework. We think we know how you make from quarks to protons, neutrons, to elements, to galaxies, to atoms, to galaxies. Clearly, we need a lot of dark matter. We don't know what dark matter is. Clearly, we want to know. Okay? And we also need large CP violation. At this point, neutrinos look promising. We will know in a few years. Expansion of the universe. I told you about the Hubble tension. I also told you about this accelerating phase with the dark energy. We don't know what it is. We don't know how to resolve the Hubble tension. Clearly, we need beyond standard model physics. And that's why cosmology is important. And we have entered this precision cosmology age. There are many, many more measurements, much better data, and they reveal more questions. So more questions lead to more surprises, more questions, more observations. This is really nice. This is exactly what I meant by golden age of cosmology. Okay, I'm done, but I just like to show you some of the students working in this area now. The one here, you probably cannot even see his face, but in case you go to South Pole, visit him. Kenny Lau is from our group. He did his MPhil here. Now he's a PhD student at Minnesota. He's building this BICEP telescope in South Pole. And he told me that within a few years, they will know whether inflation is correct or not. They would either rule out inflation or support some of the inflation models. So this will be very, very important. Okay, I'm done. Sorry for overrunning. And of course, I welcome questions. Yeah, please just speak out.
Hi, Professor Chu. Thanks for your very nice talk. I have a question that when you introduce the dark matter, you use it to tell us how the universe formed in the small scale. But will this assumption of dark matter affect the formation of other matter in early age? For example, in the initial 3 minutes. And also, as you said, the wave function of the dark matter, the wavelength is very large. Will it exceed the initial size of the universe? And that's my question. Thank you.
Okay, thanks. 2 questions, really. Okay, so I only told you very, very briefly about this BBN calculation. Okay, So you're completely correct to say that I did not mention the role of dark matter in BBN. In fact, dark matter also plays a very important role here. I told you about the competition between neutron decaying or being captured by protons. Right? Now, this competition is also heavily dependent on the expansion rate of the universe in this first 3 minutes of the universe. Okay, and the universe expanded very fast. Then the temperature dropped very quickly, and then most neutrons will be captured by protons. There would not be enough time for beta decay, because beta decay takes the half-life is about 800 seconds. Okay? So if the universe expands very slowly, then most neutrons would decay away. And this competition affects all the abundances of the elements. So in an indirect way, these abundances also measure the expansion rate of the universe at that time, and the expansion rate of the universe also depend on the abundances of dark matter, because the Friedmann equation, which let me go back here, the rate depends on the energy density of the universe, including the dark matter. Right? So if you did not have dark matter, the universe would have expanded much slower, and we could not explain the abundances we saw today. So even there, in the first 3 minutes, dark matter is very, very important. Okay. Now the second question, if it's fuzzy dark matter, it has a long wavelength, will it restrict the size of the universe? Well, the data today tells us that universe has always been infinite in size. Okay? So let me come back to this picture. Today we know that the universe is flat and there's no boundary of the universe. So the universe has always been expanding, but it has always been infinite in size also. So the de Broglie wavelength of the matters in this universe would not restrict the size of the universe at all. Okay.
Thank you.
Thank you. Any other questions?
May I ask a follow-up question?
Sure.
Yeah, so you said the universe is always infinite in size. How about at the Big Bang? Does it have any size? Or...
Yeah, so good question. So it's not intuitive. Okay. Now we can only say anything based on solid physics, solid theory, and solid observations, all the way to about the first 10 to the minus 5th second. Right? We don't know yet whether this really was this inflation. And so we really could not tell. Well, your question is, what about the size of the universe at the Big Bang, right? So the first, you have to define for me, what do you mean at Big Bang, right? We usually call Big Bang to be the phase after the inflation, okay? But if you're referring to this initial point when the quantum fluctuations got amplified to going through the inflation phase, then we don't know, because we don't really have the quantum gravity theory to describe what happened at this time. Don't know, right? We can only make use of general relativity all the way back, but not too far back, because you know the space-time curvature will be too high and the fluctuations will be too large. We don't know what happened. So I don't know how to answer it. Nobody knows how to answer that question.
Okay, thank you.
And in fact, the Friedmann equations will break down Did Leon have a question?
Yeah, I do have a question. Something would be a little bit beyond today the slides, but yeah, but because we have discussed about a little bit about CMB, so I always heard about a terminology from cosmologists is about so-called CMB B mode. So what's the what is the importance of the CMB B mode detections to cosmology?
Right. I really didn't have time to talk about that. But that's exactly what Kenny is trying to do in South Pole. So this instrument is really the main target is to measure the polarization of the CMB photons. Okay, so CMB photons are light, so there are polarizations, right? And there are two independent polarizations. You can decompose them either like X and Y, or you can decompose it in some other ways, okay? But there are always two modes, right? The popular way to decompose it in cosmology is into E mode and B mode. B mode would have patterns that look like the curve, okay? To make a long story short, basically, if inflation is correct, this very large acceleration of the expansion of space must generate a lot of gravitational waves. And the gravitational waves would make imprints into the CMB patterns. The B mode is nice because the B mode is not contaminated or much less contaminated by the later universe. Okay? The E mode, on the other hand, is much, much more contaminated. So if you see B mode, then maybe you are seeing the gravitational imprint on the CMB. And that would be the first direct confirmation of inflation. That's the significance.
Okay, thank you.
I have a question about the density fluctuation in the early universe. So it is predicted that upon this density fluctuation, primordial black hole will be formed. And I wonder, besides this primordial black hole, in the early universe, when there's going through some density fluctuation, would it be possible for those hadronic matter go back to the gluon quark matter phase?
Good question. Yeah. So yeah, I really don't know. It was very popular, particularly popularized by Hawking himself, that the primordial fluctuations could produce a lot of primordial black holes. Okay, and they might be part of the dark matter as well. Okay. However, again, we are getting into this part of the universe, the inflationary part, that we are much less certain of. There are hundreds of different versions of inflation models, and it's not clear at all what happened. So we don't know yet how or whether indeed the quantum fluctuations get amplified into classical fluctuations, producing the anisotropies we see in CMB. That we don't know yet. Okay. Now back to Juno's question. In the quark-gluon phase transition, could there be large enough fluctuations that we have backward? Okay, so even though most matter cool down from the quark-gluon phase into protons and neutrons, could we have local fluctuations so that we have quark matter sort of nuggets. Okay, that's what they call. Okay, indeed, people talk about that. Okay, there could be local regions in the universe even today that we have quark matter. People even talk about strange stars. There might be neutron stars, maybe the cores of them are still quark matter. Okay, so indeed, some of our students also work on that, work on those. You could ask yourself, what are the signatures of such objects? Okay? So if you do have a quark star somewhere in the universe, how could you tell whether it's indeed made of free quarks or protons and neutrons? So the possibility is there, and we need to calculate and tell people how to distinguish between hadron stars and quark stars. That's also something we do here.
I see. So can I say that even though if this kind of matter form in the early universe, there's no way that can leave a signature that could be detected by now?
Oh, no. There are ways, but they are difficult. Okay. So just give you one example. If you have a quark stars, its oscillation frequencies or the oscillation modes will be different from neutron stars. So presumably, if you have an event of two quark stars merging together, they emit a lot of gravitational waves. Then by detecting those gravitational waves, you might be able to tell. Okay. Now, on the other hand, it will be much more difficult to tell whether that star was a quark star from the beginning or much later in the universe. Maybe something happened and became a quark star. That we don't know. Okay? So whether that's a leftover quark matter from the Big Bang or some quark star made in the late universe, that is much more difficult.
I see.
Okay.
Thank you. That's interesting.
In fact, it's the same questions for black holes. Okay? You see a black hole, black holes are all around. How do you know whether it's primordial or produced in the late universe after stellar evolution? Okay? That's also difficult. Any other questions?
Hello. Hello, Dr. Chu.
Yeah.
So I have a question about the Hubble constant tension.
Yeah.
You mentioned that in Terry's work, you two found that there's a direction preferred in the universe. So the implication is that the Hubble constant might depends on the direction. So I would like to know if it could be the case that the Hubble tension also depends on distance, or is there a way we can separate whether it is the angular dependence or the distance dependence? I don't know whether this question is valid or not.
Yeah, it is valid, and I haven't followed the details of all the local measurements. Okay? But I think Terry has found papers claiming that the supernova measurement of the dark energy of the accelerating expansion, that also has a preferred direction. I think Terry is here. Terry, speak up. Can you tell us more?
Yeah, I think there is also currently a dipole of the Hubble constant measurement from supernova. Let me see. So I think there was a paper. Sorry, I can't find it now.
So even using only the local measurement, there is a dipole.
Right, yeah.
So does that mean the supernova data itself already gives a very large range of the Hubble constant?
Do you know, Terry?
I think the range is not that large. So not maybe the maximum deviation is only maybe 2 or 3.
Right. Yeah, that's somewhat reflected in this uncertainty. So it's not like the 6 units between CMB and local. Okay.
Then back to the question, is there a way to distinguish whether there is an angular dependence or any distance dependence on the Hubble constant?
Okay, now, so first of all, we don't call it Hubble constant anymore because this expansion rate, it is assumed to be independent of space, but it definitely depends on time. Okay, so
Right.
not a constant, so we call it a Hubble parameter. Okay. Now the question is, whether we can tell the difference between its dependence in the angle in the sky, in distance to what?
To say, so we're observing on the Earth. So what I'm thinking is that if you have a direction dependence, it might be happen that the universe has a preferred direction. So that's the implication.
Yeah.
But then if we have a distance dependence, that would mean the universe is not that uniform as we assume.
Okay, now the local measurements, of course you can, local measurements usually means nearby objects, okay, supernovae and other stellar objects maybe. Then you can maybe tell whether there's a distance measurement. Maybe your maybe it really depends on the supernovae, okay, how close it is to us and so on, right?
Mm-hmm.
But that should not be a measure of H naught, because H naught should be the expansion rate today, right now, here. Okay? So even though you measure different distances, you should really extrapolate to 0 distance. That is what we meant by H naught. But your question is still valid. Maybe there's some systematic error in the measurement in this extrapolation. Okay, that's perfectly possible.
Nice. Thank you. One more question. So when you talk about the n-body simulations regarding how we can obtain the structure of the universe, the large scale structure of the universe today, and then we put in those parameters and then do the n-body simulation, I suppose there will be some initial fluctuation that you have to manually invoke in the program in order to generate those simulation.
Right.
And I would assume that the final product of the simulation, the large scale structures will very depend on the fluctuation, the form of fluctuation that you invoke initially.
Right. Right.
How could you tell the difference between whether the effect is more on the fluctuation that you manually input, or it has a larger dependence on the parameters that you input?
Right. Usually we assume a form, it's more or less like a power law form, and the power law index is a cosmological parameter. So you can measure that parameter by CMB.
Okay, so the parameters are those index which can be obtained from observations.
Right. And so indeed, Peebles grained picture that galaxies are seeded from the CMB fluctuations. That has been verified. And Peebles got his Nobel Prize. Okay? But this is only half of his grained conjecture. The other half is going from the CMB fluctuations back to the primordial quantum fluctuations. That is a much more difficult question, and that depends on this so-called inflationary phase. That is going to be a hot topic in the coming future for cosmological research.
I suppose that in the n-body simulation, the starting point is after the inflation phase.
Right.
So how could you tell how much perturbation or how much deviation from the, I don't know, the density or the temperature is needed, or whether I can tell those fluctuation is correct or not?
Right.
The magnitude and the I don't know how to say. It's like the space dependence or something like that.
Right. So again, this is measured. Okay? So from the fluctuations in CMB, you can evolve to another redshift, still very high redshift, okay? Using the linear equation. So there's only linear growth between here, which is redshift about 1000. You can evolve it all the way to redshift maybe 100, okay? There's still no nonlinear growth yet. So you can safely use a linear boson equation, and everything is under control, okay? So you don't need to assume initial fluctuations. You start from here, you evolve from redshift 1000 to about 100, and then you start your n-body simulations from redshift 100 to the next.
So the initial fluctuation is directly taken from observation, actually.
Well, I should say the power, the distribution, okay? You don't need the spatial every point. You only need the statistical description of this situations, power spectrum, basically. Okay, so that's taken from CMB, no problem.
Okay, and a follow-up question is that when we look at those n-body simulations, what is the qualitative way to say that it matches the large-scale structure of the universe?
Yeah.
So I have some results in computer, and then how do I quantify those structure in order to compare with the observation?
Right. Good question. So we usually do calculate some statistical quantities. Okay, the simplest one being the power spectrum again, which is a Fourier transform of 2 points correlation. Okay, so it's quite intuitive. So start with 1 point. Let's say you have a high density, okay? And then you look around at some fixed distance to see what's the probability of finding another high density, okay? Mm-hmm. So then you have these 2 points correlation as a function of the separation. You do a Fourier transform, you get a power spectrum. There's a quantitative and statistical measurement. You do this for the simulation and for the observation, and then you can compare the power spectrum. Okay. Now you can do more than that. You can do 3 points correlations, 4 points correlations, and so on. You can clearly do that for your simulations, but for observations, of course, you get larger and larger error bars. So, but in principle, you could do all those.
So currently, they only compare up to the 2 point correlation.
I think they have done more. They have done the 3 points. Those are called eye spectrum and so on.
Thank you.
Yeah, good questions.
I'm sorry, I have a follow-up question following Leon's question. So I forgot what he asked, but in your answer to his question, you mentioned something like, if we can probe the B mode of the CMB photon polarization in the bicep free, we can, that might be a evidence of the imprints of the gravitational wave from the inflation.
Right.
But then during the inflation phase, or even before the inflation phase, we cannot use the current physics model to say anything about that, because I guess we will need quantum gravity. So by what do you mean by we can see the imprint of gravitational wave, or even if we detect them using the current theoretical models or theoretical framework, we cannot resolve anything from that?
Okay, so let me clarify, okay? Inflation model could be built using just Friedmann equation, no problem, right? So in fact, if you go to the Friedmann equation and put in a large cosmological constant, you get inflation. Right? So there are many different versions of inflation models, but usually they involve some phase transition. So somehow the cosmological constant was very large in some early universe, and then it becomes very small like today. Okay? So you could describe this inflation using GR, using Friedmann equation, no problem. But once you have a significant A dot dot, then you must generate gravitational waves. And so that's a very general statement. No matter what details or inflation model is, once you have this exponential growing expansion of space, you must disturb space-time in such a way that you generate a lot of gravitational waves. And these gravitational waves should still remain even today. Okay? They remain during the CMB phase, so that in large scale, the distribution of the CMB fluctuations should reflect these gravitational waves passing around. And they are the B mode that people look for. Is that clear enough? So when I said that GR would break down and so on, I was really referring to the initial phase of inflation, how it goes from quantum fluctuations to something more sizable.
Okay, so and the imprint of the gravitational wave is already after that phase.
Yeah.
So okay.
Yeah, much later actually.
Okay, thank you.
May I ask about the Hubble tension again?
Sure.
So we now see that, I mean, we kind of see that the Hubble parameter has a so somehow that a preferred direction. What kind of implication does that? Is that, I mean, the universe has a center, I mean, expand with a center, or does it expand in an ellipsoidal way? And the other thing is, now that we see a clear linear relation, does it tell anything?
Right. So in our paper, we concluded that there are two possibilities. One, which I think is a larger probability, is a standard Planck analysis of CMB data has some unknown systematic error. Okay, so they did not know about it. Right? I think it's quite clear to be a possibility. Otherwise, if even though you have all these systematic errors, they don't produce a preferred directions. And then this would imply a preferred direction in the universe somewhere along here, in this blue cross. We cannot tell from the data why there is such a preferred direction. There are many possibilities. Okay? Even within general relativity, there could be anisotropic but homogeneous universes. Okay? So they're called Bianchi type universe. So they are solutions of GR. They could be there. Okay? One very famous example of such kind of universe is a rotating universe. People investigated rotating universe for a long time already. There's a famous mathematician by the name of Gödel. He's a good friend of Einstein. And they work together at Princeton. I think it's on Einstein's 70th birthday. Gödel produced a rotating universe solution of general relativity as a birthday gift to Einstein. So you could actually have such kind of universe. You could have a rotating universe. That's one possibility.
Can I ask something about this rotational universe? Is it rotating in a 3D sense or in a 4D sense? Because if it is rotating in a 3D sense, I would imagine there is a rotation axis and the expansion would have an angular dependence instead of one single preferred direction as shown in this plot. So how do I imagine this rotation in universe thing?
Yeah, again, there are different types of rotating universe solution, but in the original Gödel's type, that universe actually did not expand. That's why people usually ignore it. Okay? But it's a 3D rotation, so there is a preferred direction, preferred axis, rotational axis.
So this preferred direction would then be the rotation axis.
Yeah.
Okay. Wait, no.
That solution cannot account for that. There's no expansion in that solution. So it's just a mathematician's toy model.
Wait, but if there is a rotation axis, then I would imagine there is a pole, like a north pole and a south pole. Then shouldn't it be another preferred direction in this plot?
Yeah, that's why we fit it to a dipole. Okay, I told you it's a dipole. So this is only showing one direction of the dipole.
Thank you.
Okay, Juno, should we stop here then?
Yeah, I think there's no more question. Maybe we can stop here. And thank you very much for the talk.
Thank you.